Hi folks, in this video I want to talk about high energy phosphates. So the compound that I've drawn here contains two phosphates chemically joined together by what's called a phosphoanhydride bond. And in fact, this compound contains two phosphoanhydrides. It contains this one here and also this one that's right here. So why do we call these, what's so magical about the phosphates? Why do we call these high energy, I'll put that in quotes here, high energy phosphates? There's nothing particularly dramatic about the actual bond. But what is dramatic is the collection of these atoms all together. Notice when you have two phosphates put in close connection to each other, we now have 4 negative charges all sort of packed into a very tight space. So when you hydrolyze a phosphoanhydride bond, so if we take water and do a hydrolysis reaction where water is going to react at one of the phosphates, and let's say we break this phosphoanhydride bond, the product that you get out now would look like this. Here I would have my phosphate on the left plus another phosphate. Okay, so what I've done is in the process of hydrolysis, we basically relieved the repulsion of these 4 negative charges all being packed into one tight space. So these desperately sort of want to push away from each other because they're repelling their same charge. When you hydrolyze these types of bonds, that relief of the repulsion energy ends up giving off a considerable amount of energy. So the hydrolysis of phosphoanhydride bonds releases energy. And in chemistry, when we talk about the amount of energy that's produced in a reaction, we typically are going to use the unit of what's called kilocalories or calories. Or if you're using the SI units, you'd use joules or kilojoules. For our class, we'll just use kilocalories. And again, a calorie is the amount of heat that's required to raise 1 gallon of water 1 degree Fahrenheit. So that's how much a calorie is. In essence, the release of these phosphates now is going to generate a certain amount of calories. In general, hydrolyzing a phosphate bond tends to give off approximately 7.3 kilocalories per mole of phosphate. And I'm putting a negative sign in here. When you talk about the release of energy, the negative sign means releases energy. If I had a plus sign there, so in other words, if I was to go in the backwards direction, take these two phosphates, stick them together to make the phosphoanhydride bond, it would require that same amount of energy, a plus 7.3 kilocalories per mole. So these high energy phosphates are important in a very important molecule called ATP. So we're going to show the structure of that one next. All right, so one of the molecules that we really need to learn a lot about is this molecule that I've drawn here called adenosine triphosphate, or ATP. So notice that ATP actually has 3 phosphates connected with several of these phosphoanhydride bonds. There's then a ribose sugar, and then I've just put the base A up here. I haven't drawn the full structure of adenine. So this entire structure, we'll just put sort of a bracket here, the entire thing would be called ATP. Now, if I were to use water to hydrolyze this first phosphate here and break this bond, this would then chop the phosphate off and then leave me with the rest of the molecule, which is called ADP, adenosine diphosphate. Likewise, if I use another molecule of water to chop off this second phosphate to give me now from here over, this would be called the molecule AMP, or adenosine monophosphate. And lastly, if I use water to chop off this last one here and just leave me over here what's to the right, this would now give me adenosine. Okay, so each of these phosphates has a particular name associated with it. Let's just show that here. When you are talking about the 3 phosphates of ATP, the first phosphate that's closest to the sugar is called the alpha phosphate. So we just write the Greek letter alpha. The middle one is called the beta. The terminal one is called the gamma phosphate. So in converting ATP to ADP and vice versa, we would be either taking off the gamma phosphate or putting it back on. And that interconversion releases energy. So if I go in the downhill direction, that's going to give me minus 7.3 kilocalories per mole of ATP being converted to ATP. Now if I want to go in the reverse direction, I'd have to put plus 7.3 kilocalories per mole into ADP going in the reverse direction to make ATP. Okay? So that's if I chopped off the gamma phosphate. If I were to have the gamma phosphate off and start with ADP and now chop off the beta phosphate to give me AMP, that also liberates approximately 7.3 kcals per mole. Finally, if I was just at AMP and I wanted to chop off this alpha phosphate just to give me adenosine, because I only have one phosphate and there's no negative charge repulsion here, I don't get quite as much energy. This is actually minus 3.4 kilocalories per mole. But the bottom line here is that ATP has these phosphoanhydride bonds, which potentially can liberate a tremendous amount of energy. All right, so what we'll see here in just a little bit, the last section I want to go over, ATP is sort of the energy currency of the cell. But there have to be molecules with more energy than ATP in order to make it. So I'm going to show you a couple molecules that even have higher energies of hydrolysis that can actually make ATP. All right, so in this last section of the high energy phosphate video, what I'd like to talk about are molecules that can actually drive the synthesis of ATP. So in this little table, what I've got here is I've started with ATP here. So the hydrolysis of ATP going to ADP and inorganic phosphate, or PI, gives off negative 7.3 kilojoules per mole. But if I want to make ATP, I have to have molecules that have a higher energy of hydrolysis than ATP itself. Two of the primary molecules that do this are phosphoenol pyruvate, or PEP, and another molecule you might have heard of, creatine phosphate, or CP. Let me just quickly draw out the structure of phosphoenol pyruvate. Okay, so this is the structure of PEP. So if this phosphate here is hydrolyzed, so we break this off and we now make release this phosphoanhydride bond, or this is actually a phosphoester bond, we will convert PEP into the molecule called pyruvate. And this molecule actually, or this hydrolysis reaction, is probably one of the most energetic in our cells. This actually liberates close to minus 14.8 kilocalories per mole. So it's almost double, or a little bit more than double, what the hydrolysis of ATP is. The other molecule that could potentially be hydrolyzed is this creatine phosphate. Let me draw that structure for you. Okay, it's kind of an unusual structure. Oops, there's an oxygen there. Or no, there's actually, yeah, that's right. OP double bond O. So if you hydrolyze creatine phosphate, and actually there's not an oxygen there, sorry. There's just a bond right across there. This is actually not an anhydride, phosphoanhydride. This is a phosphoamide bond. So if water hydrolyzes this, we then get the molecule here, which is just called creatine. And that molecule, if you hydrolyze it, gives off 10.3 kilocalories per mole. So these two molecules are referred to as high energy phosphates, but they have what's called a higher transfer potential than regular ATP. So these two molecules would be classified as a high phosphate transfer potential. And they can be used to synthesize ATP because their hydrolysis yields much more energy than just the simple hydrolysis of ATP into ADP. So these molecules are going to come up a little bit later in metabolism when we're talking about, say, glycolysis and other metabolic pathways when we have to make some ATP. All right, so that summarizes high energy phosphates. The bottom line is when you hydrolyze one of these phosphoanhydride bonds, a tremendous amount of energy can be released. And ATP is sort of the central molecule you need to think about when we're talking about phosphate hydrolysis. All right, I hope that helps. Good luck.